Hello, and thank you for watching this presentation. Today, I will show you new results on the 2019 Ridgecrest earthquake that illuminate surface slip variations and all-fold deformation patterns using high-resolution optical image correlation. On those two pictures of the surface ruptures, you can see that the surface deformation after the earthquake distributes within a fold zone that changes in width. It can go from a few meters to several hundreds of meters and sometimes even kilometers. We also know from other studies that deformation can also distribute outside of the fold zone, and it's very difficult to see and to measure on the field because you have no specific markers like folds. So the primary issue in this study is to be able to measure this distribution of deformation inside and outside of the fold zone. First, to answer the question of what is the total amount of surface deformation after this earthquake. Then we address the issue of why is the deformation localized at what point of the rupture and why is it so widely distributed at other places? What are the differences in the mechanisms of deformation and how can we quantify this? So the Ridgecrest earthquake occurred in July 2019 in Southern California. It is located east of the San Andreas Fault and just a few kilometers north of the Garlock Fault. You have no historical earthquakes on the Garlock Fault, so it raises the issue of potential seismic hazard in Southern California. The sequence is composed of two earthquakes. You have a foreshock of magnitude 6.4 that occurred on the 4th of July. And you have then a main shock 34 hours later of magnitude 7.1 that occurred on the 6th of July. So the sequence ruptured through cross-cutting faults, as you can see on this figure, with two different azimuths within 34 hours. And so by analyzing the surface deformation pattern, we seek to have more information on the earthquake mechanism itself. So to do so, we use the correlation of high-resolution optical images. All the images we use are at 0.5 meters ground resolution. We have a set of pre-earthquake and post-earthquake images composed of worldview and Pleiad images. For both scenes, we have at least 2 or 3 images, so we are able to calculate digital surface model and do the auto-rectification of the images by ourselves. We do this work using the Micmac correlation software that is developed between IPGP and IGN in France. Finally, once we have corrected the images, we can do the horizontal correlation using Micmac as well, that enables to find the position of a pixel in the X and Y directions between the two acquisitions. And so we have the horizontal displacement field during this earthquake. These methods enable to keep the input resolution of the images, so we have 1 point of measurement every 50 centimeters, and also we are able to detect displacements down to 10 centimeters in the case of the Ridgecrest earthquake. So here are the results we have for this rupture. You have on the left the north-south component of displacement, and on the right the east-west component of displacement. You can recognize the two orientations of the rupture, this one, which is about north 150, and this one, which is about north 42. The displacement field is very heterogeneous and complex. You have many geometrical complexities, like this photopark basin here, those cross-cutting faults to the north, the junction, for example, also between the two ruptures, etc. You have, in total, more than 50 discontinuous faults that ruptured during the earthquake. And when you do the comparison with the work that has been done on the field, you see that you have a very good fit between the trace of the fault on the field and what we find with our displacement maps. You still have a few faults that were not mapped on the field that I indicate with the small white arrows, but this is in a very few cases. However, our method is also able to calculate diffuse deformation in addition to localized deformation. The diffuse deformation corresponds to the part of deformation that occurs outside of the fold zone and that is not characterized by any slip offsets and localized feature at the surface. So if you compare the AA prime and BB prime profile in this area of the rupture, you can see in the case of the AA prime profile, just one localized slip offset, meaning that you have one fault that accommodates deformation to the surface. However, on profile BB prime, you see that you still have one fault, but you have a large diffuse deformation gradient. When you zoom in this area, you realize that you still have this small fault here, which accommodates about 50 centimeters of displacement. And then for 1 kilometer, you have this gradient in color that correspond to that diffuse deformation, which accommodates about 80 centimeters of displacement. So this is the important thing that we can measure with this method, and that has to be considered into the total amount of deformation after this earthquake. So we will first look at the north into an area where you do have diffuse deformation, but you also have complex faulting. So let's have a look to this place to the north of the rupture. You can see on the zoom of the displacement map on the right, still in the east-west component, that you have a series of sub-parallel faults oriented north 42, so quite similar to the foreshock earthquake, but also almost perpendicular to the direction of the main shock earthquake, which is represented by this dashed line. So if you trace a displacement profile across the main shock orientation, you see that you have only diffuse deformation in that place, meaning that you have no right lateral fault that reach the surface, and you have only diffuse shear. So the primary fault is blind and remains at depth. However, to the surface, you do see those north 42 faults. And when you trace a profile across all these faults, you see that they accommodate left lateral displacement. However, when you do the cumulative slip from C to C prime, you see that you have no finite deformation associated to that fault system. So it means that those faults must accommodate only rotation due to that right lateral shear. You also see the similar pattern in this place here, where I used to show you the BB prime profile just before, and also to the southern end of the rupture. And so if you try to explain this mechanism, you can think about something like bookshelf faulting. It is a mechanism that has been recognized in multiple tectonic contexts at different scales, and that could explain the location of those faults and the displacements we measure on those faults. This bookshelf faulting behavior with orientation north 42 has been recognized as 3 places on the rupture, but also in the seismicity, it has been shown that this orientation is also localized at depth at many places. You have the foreshock, but you also have all those big faults to the north and also in the center. And if you do a cross section across, you see that you have also those faults at depth. So we propose that those faults to the surface are associated to a regional basement fabric that ruptured during the Ridgecrest sequence. And so we want to understand further what is the influence of this basement fabric on the general displacement pattern. To do so, we measure the amount of localized and diffuse deformation all along the main shock rupture from the north to the south using a series of displacement profiles. So you have the following profile is an example across the pull-apart basin, the CC prime profile here. And you can see that you have 3 faults that accommodate deformation in this region. You have fault number 4 to the west, fault number 6, and fault number 5 to the east. The faults are located in this picture. So the total amount of slip accommodated by this profile in this region is 3.14 meters. However, you see that you have 3 different faults offset that accommodate smaller amounts of slip, and you also have some diffuse deformation between fault 6 and 4, and also a little bit between fault 5 and 6. And so we measure all those different amounts of slip on the faults, diffuse deformation, and total slip, and we construct the following diagram for the whole rupture. So in this figure, you have the total fault slip curve, which is in black. And you see that you have the maximum slip of the rupture at the center, roughly around the epicenter, which is here at 0. In addition, you have the fault slip curves for all the slip. So for example, fault 5 is the one I have shown you before in red. And you have the corresponding field data points from Duros et al. With the corresponding color. And you see that you have a very good fit between the field data and the fault slip curves, because the fault slip curves are always fitting the maximum data points for all the faults. However, you see that the total displacement profile is well above those measurements, because you have about 30% of the deformation that is diffuse. This diffuse deformation is indicated in gray in this plot. So if you also want to compare the total displacement distribution with what has been done in previous studies to be sure that our methods is a good method to measure surface deformation, so we took the predictions of surface slip from kinematic inversions. So we have multiple kinematic inversions here based on various data like IMSAR, optical, GNSS, and seismology. And for all those inversions, you see that the surface slip prediction is fitting quite well the pattern that we measured with our optical measurements. So it means that the total displacement profile as well is quite accurate. So the diffuse deformation budget also is must be accurate. So now, if you try to look at variations in the displacement pattern along strike the rupture, we compare this plot here, the surface displacement budget, with the rupture map from the Ross et al. You have the corresponding color between the different faults and the different fault slip curves. And so what we see at first is that we have three major domains with different patterns of displacements. You have a first domain here where you have almost only diffuse deformation budget. This is where I have shown you the bookshelf faulting behavior previously. Then you have a second domain where you have the maximum slip at the surface, where most and almost all the deformation occurs on different faults. So you have about 10 faults in this area that accommodate slip. And finally, you have that third domain here where the slip budget is very constant, and you have two faults that accommodate most of the deformation. You have just a small secondary fault, but that do not accommodate more than 20 centimeters of slip. And when you compare this distribution with the geometry of the fault system, you see that you can also divide the fault system in three different segments. The fault segment consists in those series of left lateral fault to the north and oriented north 140 in the middle. Then you cross a major geometrical barrier, which is this 2.5 kilometers large pull-apart basin. After, you enter an area with a slight different azimuths and where you have a very complex surface rupture with many faults. After, you cross the junction with the magnitude 6.4 earthquake and you enter the final area, which is oriented north 134, which is quite simple with those two primary faults connected with a jog. This is where we used to have the BB prime profile I have shown you before. And so we propose that there is a segmentation of the rupture and that each fault segment has different characteristics of displacement pattern. When you try to compare to the distribution of slip at depth that we know from kinematic inversions, we also find this same segmentation at depth. So this is an example of slip distribution from Wang et al., but this pattern is also found in other models. And you can see that you do have three sub-events at depth, roughly located under the three segments we inferred at the surface. So however, we see a fault gap between sub-event 2 and sub-event 3, which is located just after the connection with the magnitude 6.4 rupture. So we were wondering why do we have this fault gap at this location? And when you do a sketch and you look at the location of the two systems of fault, you see that this part of the mainshock rupture is located in the compressive lobe of the foreshock, meaning that you increase normal stress on this part of the fault. And so as you increase normal stress, you will have less fault slip in this region of the fault. However, to the north, you see that you have decreased normal stress, and so you must favorize fault slip, and it does correspond to the area where you have the maximum fault slip. So it seems that you have an influence of the foreshock earthquake on the main shock displacement pattern. And maybe if you did not have the rupture of the foreshock just there, you would have a fault slip curve that would decrease a bit more linearly towards the southern tip than having this very strong decrease and then stable slip pattern. So now I will conclude on this presentation saying that using high resolution optical image correlation methods, we could measure with great detail along strike variations of the surface deformation, both of fault slip and of diffuse deformation. And from this, we could infer that the rupture is segmented in three different parts with different amounts of fault slip and diffuse deformation. And also that this segmentation is very influenced by the basement fabric, because you have to the north the influence of that basement fabric that will rupture to the surface and accommodate diffuse shear through bookshelf faulting, but also because the basement fabric orientation is responsible for the location of the foreshock and for this, influence that the foreshock has on the mainshock displacement pattern. Thank you for your attention.